2, 1. I'm very excited. I am absolutely excited because this is my absolute favorite concept in mathematics, the notion of a continuous function. All of my research is one way or another devoted to studying these kind of functions. This is my heart and soul right here. So I hope you're ready for the ride. Okay. So let's get going. Boom. What is the definition? Given a function defined on a set S and a point that lives in S. So note the huge difference now from where we just were. We said that function is continuous at that point A if, given an epsilon, there is a delta, so that f of x minus f of a gets within epsilon for any points in S that are within delta of A. All right. I'll let that marinate for a second, because there are a couple of key differences here with this epsilon delta definition and the one we just saw. Okay. Now, I already stressed one of them. The A we're talking about could be in the set. And the other thing is that I don't have this being strictly positive. Right, because, well, there are things in S that are equal to A. A itself lives in the set, so we can no longer enforce that. Okay, so this is what it means to be continuous. Given an epsilon, there is a delta. Right? So essentially it's saying that the limit as you go to A is f of A. But note the way this is formulated, right, in order to even be continuous, we need our function to be defined at A. So A must be an element of my set S. But note, this definition right here doesn't require the cluster point stuff. So we kind of saw that with limits when I pointed that out when we talked about limits. Like, you could set this up and there's no reason to have cluster points be there. Right, it was only when we wanted to start verifying limits behave the way we expect them to that you actually need the cluster point stuff. So for continuity, we can kind of just set up this, and we don't have to worry about the cluster point stuff, because now, as we will see, it turns out we don't need to worry about it, because if you are not a cluster point, then you are guaranteed to be continuous at your point A. Always. Beautiful. Now, what would it mean to not be a cluster point? That would mean that there is nothing nearby the point A. So that would mean that there is some delta that's not behaving. So there is a delta around A so that there's nothing from S that's within delta of A. So, right, the point is then isolated in a way. So continuity is guaranteed. All right. So this is quite interesting because when we learn about continuity in calculus, we learn about it like this. Right, but to not be a cluster point just automatically guarantees the continuity. Right, because in a way in calculus, like we noted, the domains of our functions are always like intervals or some set that like everything's a sorry, hold on. Oh, I was doing so good. Everything's a cluster point, so there's no reason to even think about this concept. But anyway, so when A is a cluster point, then the calculus definition continuity comes in. And then we will conclude with this definition of continuity, which is sequences behave the way you want them to. So this gives us a way of talking about limits in context of continuity, but without having to worry about cluster points. So this, again, basically saying the limit of a function goes to where you think it should go. All right. Beauty. All right, so now that we've set it up, let's get going. All right. So if you're not a cluster point, as we've already noted, that means there is a delta, so that there are no elements of S that are within delta of A. Now let epsilon be bigger than 0. For any x that is within delta of A, this has to be true. But if x is not equal to A, that means x lands in this set. Right? Because x would be in S. Not equal to A would mean that this would have to be in that set. And we have to be in this set because of that. Well, that's contradictory. So it's got to be that x is equal to A. So f of x minus A is 0, which is less than epsilon. So we get continuity for free. So hanging out at a not limit point, at a not cluster point, automatically guarantees continuity. It's quite nice. Alright, so now let's prove that if A is a cluster point, then continuity is precisely the calculus version of continuity, that the limits are working the way you want them to. Alright. So suppose that f is continuous. So given an epsilon, there is a delta, so that f of x minus f of a gets less than epsilon for all x that is less than delta. For all x that's within delta of a. Alright, so given any x then that lives in S, so that this is true. Where's my cursor? There it is. So that is true. Alright, well then, yeah, x minus a is less than delta, so f of x minus f of a is less than epsilon, so f of a is indeed the limit of f of x as x goes to a. Conversely, hey, what's up?
I want to see it.
Okay, can I finish recording and then I'll get you some?
Yeah.
Alright. Thanks.
I'm going to measure how big I can lift.
Okay, sounds good. Okay, so suppose that we got another, not a Charlie interruption in a while, so there we go. Alright, so conversely, suppose that the limit of f of x is indeed f of a. So I want to prove continuity, so given an epsilon, our hypothesis gives us a delta, so that f of x minus f of a is less than epsilon for all x that are within delta of a, not equal to a. So, let x be an s, so that x minus a is less than delta. There are two cases to consider. Okay, if x is equal to a, then f of x minus f of a is 0, which is always less than epsilon. And if x is not equal to a, then this holds, and so that the outputs then go within epsilon, and there we go. We have our continuity. Give me 1 second. Don't, no. There you go. Do not pick up any of the big ones, okay? Alright. Down in the basement, Charlie's messing around in the other room, so I'm just making sure she doesn't get hurt. Alright. Okay, so there we go. Our calculus intuition of limits is our calculus definition of continuity is still true. Alright, now let's wrap things off by proving that continuity behaves nicely with limits of sequences. Alright, so suppose that f is continuous at A, and let x span be a sequence coming out of the set S. Alright, so very important that that's a subset of S, but anyway, while we're waiting for it to do it. Alright, so that means given an epsilon, I can find a delta, so that f of x minus f of a gets an epsilon for all x that are within delta of a, by your definition of continuity, and now, using this delta, we know that at some point the x sub n's get within delta of a, so then when I feed them into the function, they get less than epsilon. Right, so very similar to the proof that we saw that if the limit exists, then sequences are going to behave as well. Same thing is true for continuity. And note, there's very similar components to the definition of continuity and the way limits work, but right, subtle difference because for continuity, we're not worrying about cluster points. Okay, and then for the converse, that limits as a sequence is working give you a continuous function. We'll see that the proof goes... Other room, please, okay? The proof will go very similar to what we did before. Suppose you're not continuous, that means there is a bad epsilon, so that... Alright, so that means there is a bad epsilon, so that for every delta bigger than 0, there is an element in S that's within delta of A, but the outputs are not within epsilon. Alright, so that means for each n, 1 over n is a positive quantity, so I can find an element x sub n out of S, so that the output is bigger than epsilon, and the inputs, though, are within 1 over n. So that means we've created a sequence that lives in the set S that converges to A, but the outputs do not converge to f of A. So if the outputs converge always in the manner we want, that means the function needs to be continuous. Beautiful. And as we noted, and I got Olive in here too, I'm just getting bombarded while I'm trying to record this. So my cat's now harassing me. All right, so what's very powerful about this characterization of continuity is that it allows us to basically immediately reveal a wide variety of things about continuity, because we already know how limits of sequences behave quite well. So in particular, we will see that the identity function is continuous, any constant function is continuous, a sum of 2 continuous functions remains continuous, a product of 2 continuous functions is continuous. This kind of function is always continuous at any point in the domain, and we know what these are. This is, of course, a bird that does not eat a polynomial. All right, and finally, a composition of continuous functions remains continuous. All right, so all of these facts we prove, and just using the fact that a function is continuous, precisely if a sequence converging will converge appropriately when fed into the function. All right, so let's start off. Take a sequence that lives in S that converges to A. F of x sub n is equal to x sub n. So the outputs converge to A, which is exactly what f of A is equal to. F is continuous. Keep going. Take a sequence that lives in S that converges to A. All of the outputs are alpha, so that means the sequence converges to alpha, which is precisely what f of A is. Continuous. Keep going. Let x sub n be a sequence of S converging to A. We know that f is continuous, so the limit behaves. We know g is continuous, so the limit behaves. That means the limit of the sum behaves. F plus g is continuous. Same thing for the product. Boom. Look at us. We've done all this stuff for free. No work. 5, though, a little bit more work. So points 1, 2, and 4 ensure that this function, x goes to a sub k times x to the k, is continuous. Right, 1 guarantees that x goes to x is continuous. 4 guarantees that x to the k for any non-zero k is continuous. 2 guarantees that if x goes to 0, then that is continuous, because if it's 0, it's constant function 1. Okay, and then the constants are all constant by 0.2, and then the product is guaranteed to be continuous by 0.4. And then appealing to 3 guarantees that f, which is the summation of all these things, is also continuous, because 0.3 allows us to add up continuous things that remain continuous. Right, and finally, composition. Take a sequence converging to A. F is continuous, so feed it in. The limit goes to where you want. G is continuous at f of A, so we can feed in the limit, and it works the way you want it to. There we go. Beautiful. A bunch of quick and easy facts about continuity, immediately demonstrated, built off of the backs of all that wonderful sequence stuff we did. And now you kind of see the justification for why we did sequences first in analysis, whereas in calculus, right, we don't do that until Calc 2. Right, it turns out that it makes our proof lives a lot easier if we had all that sequence stuff taken care of first. All right, so we have now given a bunch of examples of continuous functions. Let's get ones that fail to be continuous. All right, so take a subset of the reals and a point A that lives in S. So we typically don't use the phrase not continuous, because K and OT, those are things in mathematics, so discontinuous is the official word for it, although I think I will occasionally slip in not continuous. All right, so let's get some examples. So the first example of a discontinuous function, a classic calculus example. To the left of 0 we're -1, to the right of 0 we're 1. That fails to be continuous at 0, and we will show that it fails to be continuous by constructing a sequence that doesn't do what we want it to do. So, for example, This sequence goes to 0, but when I feed it into my function, the outputs go to -1, but the function at 0 is 1, so the sequences do not converge, so my function cannot possibly be continuous. Beautiful. Alright, so that's kind of a classic calculus. This has a jump discontinuity, right? But mathematicians got particularly spicy in the 1800s. So specifically, a boy Dirichlet comes back, and he comes back with a function that's discontinuous everywhere. So Dirichlet cooks up the following. So the function, that is 1 if the input is rational, and 0 if the input is irrational. This function is not continuous anywhere, right? And if you visualize in your mind's eye what this function looks like, right, well, it's basically a bunch of scattered points on the line x equals 0, and then a bunch of scattered points on the line the line y equals 0, and then a bunch of scattered points on the line y equals 1. All right. So, given a real number, it's either rational or irrational. I'll show that at any rational it's discontinuous, and then basically the same proof applies for if A is irrational. All right, suppose it's rational. For any n, I can find a rational number that lives between a plus root 2 and a plus root 2 plus 1 over n, right, by the density of the rationals. Now I'll define x sub n as follows. It's y sub n minus root 2. Note that x sub n cannot be rational. If this was rational, then y sub n, which is equal to root 2. So if x was rational, then add this over, subtract that over. That would mean root 2 is a difference of two rational numbers, which would mean it's rational, which we know it's not. So x sub n cannot be rational. So f of x is equal to 0. However, by construction, we converge to A, but f of A is equal to 1, so we found a sequence that converges, but when I feed it into the function, the limits do not line up in the way that I want them to, so it must be discontinuous. Yay! Alright, like I said, you do the same thing for irrationals. There we go. So that's kind of a nightmare. So we've now seen functions that are continuous, and we've seen functions that are discontinuous. Now, a natural thing to ask is, all right, so here's a function that's discontinuous everywhere, and then we've seen functions that's continuous everywhere, so polynomials, for example. So then a natural thing is kind of like the middle ground, which is kind of the question of, all right, can we create functions? So here's a question for you, given two sets. Can we find a function that's continuous on one set and discontinuous on the other? Now, quite surprisingly, you can't do that for any two arbitrary sets. So if you have two sets that union up, you can't, in general, create a function that's continuous on A and discontinuous on B. But it's actually really shocking what sets you can pull that off with. And here's the all-time, the worst function you're ever going to see in your life. So this is called Thomae's function, named after a mathematician named Thomae, who, as far as I can tell, this is the only credit he gets, so let's give it to him, because, oh boy, is this function something else. So Thomae cooks up a function defined on the open interval 0, 1 as follows. If x is a rational number, write the rational number in lowest terms, so in other words, there's no common factors here. Now, I know we didn't formally define that, but you know what I mean. You can actually formally define it. It's the it's the representation as a m over n, where n is chosen to be as small as possible. I think I mentioned that actually when we talked about rational numbers. But anyway, so if x is rational, then write it in its lowest terms and get rid of the numerator. Replace it with 1. Otherwise, spit out 0. This absolute bastard of a function is discontinuous in every rational, but continuous in every irrational. So read that again and think about that. At every rational, it's discontinuous, but at every irrational, it is continuous. My God. So you've got a function that is discontinuous at the rationals. The rationals, by the way, are dense. They're all over the place. But here we got a function that's discontinuous at them and continuous off of them. This thing is an absolute nightmare. Now, what's great about this function, though, is actually really easy to graph it and get a picture of it. So the Dirichlet function, of course, we had a pretty good idea of what it looked like. It's just two scattered lines. The Tomei function, though, is this little beauty. Look at that. That is a sweet looking thing. So here you see 1/2, it's spitting out 1/2. So right here, that's where you got a 1/4. Right over here, that's where you got 3/4. But note, it's spitting out 1/4. Likewise, here's 1/3, and then there's 2/3, and so on and so forth. And you can go through and find all your stuff. So this is also referred to as the stars over Babylon function, because it kind of looks like a starry sky in the night, I guess. Like, you get the North Star up here. Then as you get closer to the horizon, there's like more stars clustering. So here you kind of, once you get a visual on this thing, you can kind of see that, oh yeah, there's actually kind of this crazy clustering going on down here. Now, obviously, these gaps are artifacts of its computer, so you can't get infinite precision. But you can imagine, especially down there, that down at the origin at x equals 0, these things are clustering a lot. So at the irrationals, which are all 0, right, you can kind of start seeing that, wait, at the irrationals, maybe it will be continuous. So let's actually work out the details of the proof of this. All right. So let's let A be rational, and let's get it in lowest terms. Okay. By arguments that we made before, we can create a sequence of irrationals that converge to it. So we already saw this in action in the previous proof. But that means that f sub x sub a, x sub n is equal to 0, but f of a is equal to 1 over k. So the sequences don't converge, and there we go. All right. So that wasn't the hard one. The trickier one is going to be the continuity. So at every irrational, why is this function continuous? All right, well, so first of all, it'll note that f of a is equal to 0. All right. Now take any sequence that converges to a. I'll let epsilon be positive. Okay. We can find a capital K, so that 1 over k is less than epsilon. That's just the Archimedean property coming into play. Now note, any rational number living in 0, 1, the numerator must be strictly less than the denominator. In other words, there's only finitely many rational numbers that have k as a denominator. Right? K is fixed, and specifically a denominator less than or equal to k. Right. So anything that has k as a denominator, the numerator has only finitely many choices. And since k is a natural number, right, you can only finitely go up to it. So there are only finitely many rational numbers in here whose denominator is less than or equal to k, in the sense of being the secret sauce. Because our sequence here, then, there must be a point in the sequence where either the elements of the sequence are irrational, or they're a rational number whose denominator is strictly bigger than k. Right. So the sequence is converging to A, and there are only finitely many rational numbers whose denominator is less than or equal to k. So at some point, this sequence is got to be either spitting out irrational numbers or spitting out rationals with a denominator strictly bigger than k. There are only finitely many choices. This is converging to A. So if all of these are irrational, great, we're happy. But if they are rational, it's eventually going to have to exhaust all of the ones whose denominators are less than or equal to k. All right, beautiful. So at some point in the sequence, we're either spitting out irrationals or rationals with a denominator bigger than k. Of course, this is in lowest terms. So that means any n bigger than n, f of x sub n is either going to be 0 or it's going to spit out a fraction, 1 over a number that and that number is bigger than k. Let me include that here. Okay, so either this is 0 if it's irrational, or it's 1 over q, but 1 over q is less than 1 over k, which is less than epsilon, and there we go. The sequences go, and so f is continuous at a. Absolutely amazing, right? There's a real slick proof, too, and this is using a really nice little trick here, where you've got a sequence, and, right, there are only finitely many things satisfying a certain thing. So the sequence, which is converging to A, right, it's, right, if it has to be running through all these values, and since there's finitely many of them, it's going to exhaust them, if it even has them. So at some point, it's going to have to spit out things that are different, and that forces everything to be less than epsilon, and there we go. Proof completed. Oof. So the Tomei function begins the ruination, the beginning of the existence of very weirdly behaving continuous functions. So, all right, it's gonna get worse. I've already kind of leaked it with the picture for the course, the absolute all-time worst continuous function, but we'll see. It's going to get a little bit more spicy. All right, that finishes the conversation for today. I'll see you next time where we go after the value theorems, the extreme and the intermediate.